welcome our outstanding speaker, Dr. Maria Terzi. Maria is a Women Who Codes Emerging Tech Leadership Fellow and co-founder and CEO of Malik, an AI-driven privacy and data security startup, helping people to stay safe and private online. Thank you, Maria, for being here today, and I will pass the session over to you.
So today's talk is going to be about privacy and how we can develop software that respects users' privacy. So privacy, one of the earliest versions of privacy is the curtains that we use in our homes, the blinds that we use so that the neighbors will not see us when passing by. But when you try to develop privacy into software, it gets a bit more complicated. One of the best definitions we had until now about privacy was the Delanius Adomnia guarantee, which said that anything that can be learned about a participant from a statistical database can be learned without access to the database. In other words, privacy is preserved if after the analysis, the analyzer doesn't know anything about the people in the dataset, which means that the people remain unobserved in a dataset, which is super difficult because how can you learn about people in a dataset without really watching the people in the dataset? So is it possible to answer questions using data we cannot see? Thus far, the recommended approach was anonymizing or encrypting the data. So what they told you is that if you have a data set and you want to investigate it or give it to a researcher for further analysis, you should anonymize the data. So you should remove any information that will identify a person, like the ID or the social insurance number or anything that is very, very explicit about that person. But what we found out is that anonymization doesn't work. And I will give you a few examples. One of the first times that we started realizing that this is not going to work was when the Netflix challenge went by. So Netflix announced this competition that they will give $1 million to the researchers that will create the best recommender system for Netflix. This is a system that will suggest to you movies when you are watching Netflix. So one researcher got this anonymized data set, which contained only movie IDs and user IDs. And they joined this movie, joined the ratings of the movies with the IMDb database. So they did a simple correlation. They just matched the data between them. And surprisingly enough, they could reveal the titles of too many people and too many movies from the data sets. So what they did is that they just matched two individual data sets and they de-anonymized the complete data set, and the probability of anonymization was super high. So in the 500 was like 8%. Another well-known case was the re-identification of the governor's William Wells medical records. So what happened here is that in 2012, a medical student got some medical data that have been published in the past, and she also got a voters list. So both data sets have been anonymized, so they contain no ID, no social insurance number, but just based on the zip number, the birth date, and the sex, they could identify 64% of the people in those data sets. So again, the attacker used data from two different data sets to separate data sets. Both of them have been anonymized, and they could match the people. And the same happened in a DNA study, in a research that used a DNA study, which again used the PGP profile with the voter list, and they did the same thing with a really good percentage of revealing the people. Another example, in 2006, OWL, if you remember, they shared the logs of their search engine in a competition in order to improve the search engine. Only a few days later, New York Times could spot in the dataset this lady based on her search history. So this lady was from a village, she had a dog, and she had some sort of illness, so they could really track down this person in real life and identify her. And imagine the shock of this lady when she figured when New York Times revealed this story, and everyone could see her search logs. Another example from, I don't know if you have seen this map before. If you haven't, this is the map from Strava. It's an application and bracelets that you can use when you go to have your gym, to run outside or go for jogging. And this company revealed this magnificent image to promote how many runners around the world they have and how many people are using their bracelets and their apps during their jogging. What they didn't know is that in this map somewhere, in this heat map of 30 million runners worldwide, you could clearly see in Sahara a little square. And what happened was that there was a French military base in Mali of people, of soldiers, every morning running around the square of their base for their gymnastics. And by publishing this image, basically they revealed to the world the largest U.S. military facility in Afghanistan. I don't think they knew or they could realize what they have revealed before actually someone spotting this. And this affects also a lot of companies suffering from data breaches. So privacy and data protection is super important. One of the best modern ways to preserve privacy, it's differential privacy. And this is also applicable to the latest developments of software and also in machine learning. So the best definition we have thus far about differential privacy is the one that Cynthia at Work provided in 2014. And she describes differential privacy as a promise made by the data curator to the data subject, and it goes like this. She says, "You will not be affected, adversely or otherwise, by allowing your data to be used in any study, no matter what other studies, dataset, or information from other sources is available." And this promise covers all the previous examples that we have seen of matching auxiliary information, matching datasets in order to reveal information. So speaking more technically, a perfect privacy will be a query to a database that returns the same value even if we remove any person from the database. So let's say that we have two databases. Database C contains 4 numbers, 10, 20, 30, and 5. And from the second database, we just remove the third element. One of the privacy attacks that people are using, the differencing attack, so what it does is that you first sum up all the values in the first database, and then you measure the mean, and then you remove an element from the database, as we see in the database 2, a tone, and we see that the mean changes. So if the sum of the values is changing, it means that you can constantly by removing one information, you can reveal that information. And this is one of the most usual attacks which someone can use to reveal data. The important thing here is that if we remove a person from the database and the query does not change, then that person's privacy is fully protected. That is the principle. However, can we construct a query that doesn't change no matter what we remove from the database. In order for this to work and for differential privacy to work, we require a form of randomness, a form of noise that can be added to the query to protect people and the data from differencing attacks. And there are two types of noise that we can use. We can either add noise to the function data points, to the inputs, or which is what we call a local differential privacy, or we can add some noise to the function outputs, which we call global differential privacy. And always the global differential privacy leads to more accurate results. However, the assumption for this is that the database owner is trustworthy. And maybe I can also add an example here. So when we're speaking about local differential privacy, is that, for example, you're creating a database. This database contains the ages of people. Instead of saving the exact age, what you can do is that you can put some ranges. So let's say ages from 10 to 15, you're going to put 15. From 15 to 25, you're going to put 25. And in this way, for example, with grouping ages, you don't reveal one single person information. You're adding some noise around it. Another way to do it is that you can add some probability. So let's say you, again, with the ages example, instead of saving, I am 35 years old, instead of saving 35, you can add either plus 2% or either minus 2%, which it will not make a huge difference in the global picture, but again, it will preserve privacy. One of the most popular ways as well to do it is by using randomized response. And randomized response it has been used many years ago as well, and it's also being used a lot in the social sciences when trying to learn about the high-level trends without revealing too much. It's used basically to make questionnaires about taboo behavior, so things that not many people want to answer. For example, and the way that this works is by flipping a coin and by creating, the goal is to create what we call a plausible deniability. So let's say we want to reveal the smokers in the room, but we don't want to ask the people to say explicitly if they're a smoker or not. We can ask everyone to flip the coin 2 times. If the first coin flip is heads, they should answer honestly, yes or no. If it's tails, they should flip the coin again and then answer according to the second coin flip. So yes if it's heads and no if it's tails. And this gives you like a 50% probability of getting the yeses correctly, and then another probability of getting the noses correctly. So what it does, it's adding some noise in your results, which will still give you a good result, a good understanding of what the situation is, without knowing exactly what is happening, and also by protecting the people within the data set. A similar approach, I'm again giving examples in real life, which can be used for software. So let's say we want to reveal how much money people have in their pockets. We can tell them, pick a number from -100 to 100 and add it to your true number of money that you have in your pockets and tell us the sum. So, for example, I have $20. I picked -50, so I will report -30. Again, in this case, if you have a sufficient large number of reports, you will cancel out all the noise and you will get an approximation of the actual result. As you understood also from the examples I provided, I hope, differential privacy does come at the cost of accuracy. So the bigger the sample, closest to the true population you have, then the less the noise will be in your final result, and as well the better the data will be protected. In industry, this has been used a lot from all the tech companies. For example, Google has used what they call rapport in order to find out what home pages or search engines have been used by their clients in Chrome without compromising their privacy. So you're using the Chrome browser, but you're not using Google, or you may be using Google as a search. How we can find out what search engine are you using without compromising your privacy. So without explicitly knowing that you are using the specific search engine. So what they did is that they used a sort of randomized response. And a good metaphor of this randomized response is the report is the portrait of Mona Lisa, which if you see it more closely, you will see that it's made up of bytes. And what they did is that they collected the responses from the users, but they flipped them with a probability of 25%. So no matter what your response were, it had 25% chance to be flipped in the system. So at the end, even if at this moment you cannot clearly understand what is happening, with all the metrics coming in, you could see the big picture. You could understand and get a good sense of what search engines have been using in their in the Chrome browser. Apple also have been using differential privacy in order to learn from private data, and they have been using this on the mobile devices as well. And this was easy for developing standard software, but when we started developing with machine learning, it became a bit more trickier. So if we're talking about a normal system, let's say, I just use the word normal to describe a traditional system that has a database and you make queries to the database to get data. For that, the perfect privacy will be a query, as we said, that retains the same value even if we remove any person from the database. Now, for AI model, this principle will change to training a model on a data set should return the same value even if we remove any person from the training data set. So even if we remove data of people that we have trained on from the trained model, it shouldn't change the value. But the challenge here is how can we know when the people are referenced in a data set? And again, we have the challenge of having some randomness in the training process where neural models nearly never train to exactly the same state. And to solve this, there is a technique called Federated Learning, which was, it started from Google, and is one of the most widely deployed techniques in the context of private machine learning. And it's a technique to train on machine learning models to which you don't have direct access. It has been presented by Google in 2017, and it has been a lot of research on this topic and also a lot of development implementation so that people can actually use it. So when Google presented this, they said that, okay, with the new privacy legislation in place, we have three choices. Either to not use at all the data of the users from their devices to improve our products and services, to lock the data centrally anyway, so to collect the data anyway, or to invent a new solution. And they came up with Federated Learning. So if we would like to think about this again, we had, in machine learning, we can see it as three different options. either collect the training data and train a local model. So train a model on the device of the user to detect things or to classify things, which is not great because it's very computationally expensive and you need to run it on the device of the user. And also you don't benefit from the knowledge produced from all users in machine learning. You can benefit from the knowledge of all users. So you can receive data from all users in a central server, but this would mean compromising users' privacy because you collect all their data and their personal data to a local server to then train a machine learning model and then give them back to the users. And then we have federated learning, which in which method we train a model on the device of the user, but then only the updates of the model are sent to the server, are aggregated into a new model, and returned back to the user. So we can describe this a bit in more detail. So let's say we have a lot of mobile devices, and we want to collect data from all those devices and train models to detect images or do another machine learning task. With federated learning, you have the data sitting on the device of the user, so we don't collect any data. We have a model on the device of the user, which is provided by the engineer, and we train this model again on the device of the user with the data of the user. And then we produced an updated model, but then we do not send the model back to the server because this will mean, violating the user's privacy. What we do is that we just get some ephemeral reports. We get only the updates produced, the knowledge produced for the new model. And then in our servers, we combine all those detections, all these knowledges, which is basically numbers and some features maybe from our model. We create a new combined model, and then we send this model back to the devices of the users. And you will ask me, is federated learning enough? It's not. So when they put this into application, Gboard from Google and also Apple use this in the mobile phones in order to, in their autocomplete. So you will type a sentence and the machine learning model will autocomplete it for you, will provide some suggestions. When they started using it, one of the examples was if you mention a name and the credit card number is, it was actually revealing the information that it was trained on. So we need to be more careful with federated learning. We shouldn't use it alone to protect users' privacy. We are clearly violating the principle of differential privacy about not memorizing any individual data or revealing individual data. And another example, in 2019, again, in a machine learning model that was used, they could from the gradients of training a classifier to detect things on images, they could actually at the end recover the images, which are two examples in two different cases that reveal that federated learning alone is not enough. We should add differential privacy and add some noise to protect the individual's impact on the learned models. And of course, we again need a trusted aggregator. So in federated learning, when we received the updates from the models in our global model, we will need to update the model and send it back. Another technique, one of the famous techniques that are used and very easily used and widely used is secure multi-computation. So in this approach, you can have multiple people that can combine their private inputs to compute a function without revealing the inputs to each other. So it's a concept of shared ownership. So let's say I hold number 5. I give a part of the number to Anna, and a part of my number to Patricia. So I give 3 to Anna, and Patricia, I will give her 2. They know the hidden value, which is my value 5, but only by combining their values. So this approach of shared ownership and shared governance can also protect the hidden value, because each of the parties only know their half part of the party, and this may look as a very simple example of an addition example, but this is how computation is actually performed on encrypted data. So if they multiply by 2, then we can also do more. Multiply by 2 is just a function. So if we do any function on each of the multi-party data, we can actually train the model even if the data are encrypted. And again, there was a lot of research on this. The only disadvantage of this is that it has a computational complexity. So you will need to do all those functions in order to make your computations, and then it's a bit of a challenge to also aggregate them together. And I'm not going to dive too much into homographic encryption, but we should mention it. So this is an approach to train on encrypted data without decrypting first. And this is used in secure cloud computing, in medical research as well, in encrypted search. So you can train machine learning models on encrypted data. However, and there is partially homomorphic encryption and fully homomorphic encryption. But again, we have a big computational cost, and this is used when privacy is super, super important. So the benefits is that we have a good data privacy and also security, because if you are using encrypted data to your calculations, even if you have a data leakage or a data hack, no data will be revealed to the hackers, to the attempters. But there is some complex implementation, and also the computation on encrypted data has an issue for the performance. So all the computations are slower. Privacy, developing private software, particularly when we talk about machine learning models, is definitely an open challenge. And one of the open challenges, which I find particularly interesting, is the concept of single-use accountability. So I will give you an example about this. When you go to the airport, they scan your bag in order to find out if there are any weapons or drugs or something dangerous in this bag. The current approach is to reveal all the contents of the bag in order to answer this question. But in differential privacy, what we want to do is to learn from data without actually seeing data. And the best example of single-use accountability, so for seeing exactly only what you need to see and not revealing the whole package or all the data, are the sniffing dogs. So these are the dogs that are used in the airport to check bags, either for weapons or for drugs or anything dangerous. So the dogs do not actually see the content of the bags. They don't get any information about what you have in the bag, but they detect and they provide an answer to the question that was asked. So using single-use accountability, if we achieve to use single-use accountability, we will have a lot of privacy, and most of the cases will be solved. I will give you another example. In where I live, we have those cameras in the streets that they check if you pass the red line. But what they do is that they see the whole car, they take a picture of you, they track everything. What if there was just a line? What if there was a smart line on the road, and it will check only if you pass the line when the light is green. So why do we need to collect all those data by answering a simple question that we can answer just by using a different technology, let's say? Or when detecting fires in a forest, why can't we just use a model that could detect if there is smoke and if there is the color red and orange as well in a forest, instead of observing the whole forest? And these are just examples to have you started thinking about developing with single user accountability. So developing and answering questions with only revealing the data that you need to answer that question and not violating the user's privacy. So in order to have a perfectly privacy-preserving AI, we need to, there are 4 pillars that we need to have in our minds. So the training data privacy. So we need to ensure that no one will be able to reverse engineer the data. The input privacy, making sure that the data cannot be observed by other parties. The output privacy. So when the model, making sure that the output of the model is not visible to everyone, and also the model privacy to ensure that the model itself will not be stolen by any malicious party. And to ensure privacy when developing software, we must respect 5 principles. So firstly is focus collection. Collect only what is needed for our computation. Ephemeral reports, never store anything that is not needed. I mean, don't store anything during the training process or afterwards. Encryption both at the start, during the transfer, and at the end. Access only combined data device reports, and then data reports as well. So if you're presenting your reports, never explicitly mention specific data, but provide aggregations of data. So it's like the example with the ages that we provided in the past. Or if you're talking about addresses, you can use districts or cities or even postcodes. They're way more. They protect way more the privacy of the user rather than just giving the address. And of course, never memorize individuals' data. If you need to, make sure that you use noise in the input of the model. And for all this, we have explained methods that we can use. For example, for the training data privacy, we can use federated learning. For the input privacy, we can use multi-party computation, federated learning, homomorphic encryption. For the output privacy as well, and for the model privacy as well. So when you're developing a system, it's super important to check the input, the output, and what your model does. And of course, the link between them. Here I'm providing some tools that can get you started. So differential privacy is implemented in TensorFlow. PyTorch also provides an implementation for multi-party computation and federated learning. Apple has provided an on-device machine learning kit that you can use in developing applications that sit on the device and learn on the device. And you can find all those great tutorials at the links provided here. Thank you so much for your time and your attention. And of course, I'm happy to answer any questions that you may have.
There are a couple questions that I have. And one of them is, I noticed that when you were putting up the resources and talking about like what kind of information you could use and what kind of machine learning model you could use to basically answer those outputs. I noticed that federated learning came up the most. Would you say that federated learning is the most flexible method in terms of privacy and security?
Absolutely. So federated learning is definitely the future when it comes to machine learning, because it gives you the best of, of both worlds. So before federated learning, we used to train models on the device of the user. But this sometimes is very computationally expensive, and it harms the device, and it takes a lot of time, and it uses your battery. So as a user, you don't really want that. And at the same time, if you send the model on the cloud, it's super complex to combine the models, and also it doesn't respect privacy. So as a user, without federated learning, the model will be trained on your input, but you will not benefit from the training that can happen on other people's devices and the knowledge produced on other people's devices. With federated learning, as we said, the model sits on your device, so none of your data will ever leave your device, but only the parameters, the tuned parameters of your model will be shared to a trusted aggregator, and the aggregator will get a new global model and update all the users with the new model. I definitely see federated learning as the future. We also have been using it in my startup where we detect spyware. So we have classifiers running on the devices of the users, and then everyone is benefiting from the spyware detected on an individual basis from the global model.
I think that's really, really helpful. And I think that's really insightful to know that you see that as kind of the future in terms of privacy and security in the machine learning space. Daria asked, from your experience, how big should a data set be to compensate the noise?
Yeah, there is a measure on how to calculate the level of privacy that has been achieved. I can definitely share more details about this. I don't know where it will be the best place to share them, maybe in the Slack of Women Who Code somewhere. But there is a measure that you can do. So when you develop your system, you will check this trade-off of accuracy, noise versus accuracy, and you will see how well the data is protected with how much noise you add. I mean, if we want to speak like very generally, the bigger the better. So the more data that you have, this allows you to add more noise to your system and better protect the users. If it's a smaller scale, typically you need to be a bit more conscious with the noise that you add to get it. But there is a formula that you can use to check this.
It's really helpful. One of the things Christine asked was, she said specifically, I'm not sure if I understood multi-party computation. Is the privacy of MPC guaranteed based on hiding the source or actual data behind a function, and therefore revealing how the function works won't compromise privacy?
Yeah, it's guaranteed based on hiding the value. So let's say that I have this value, number 5, and I don't want anyone to know about it. So number 5 can be like a combination of numbers. It can be my ID number. It can be anything. So let's say that it's my ID number. So I give part of my ID number to someone, and then another part of my ID to someone else. So only when the data are matching, you will be able to reveal those, to reveal my complete ID address. Another example I can give you is that when we have been building the database for COVID in Cyprus, we had a database, and the university I was working for was instructed to hold the positive cases of COVID. But we wanted to do it in a privacy-preserving way. So what we did is that we kept part of the information in one database and part of the information in a completely different database. And only those information, only when being matched, they could make sense to someone. So if we had a hacker, for example, hacking one of the databases, they will have to hack the other one as well, and also hack the way that we found to connect those databases to actually reveal the personal information. I hope this makes a bit more sense.
Yeah, I think that was a big help. And I liked how you talked about basically the multi-hacking approach. So by keeping things basically separate, someone would have to go to multiple areas. One of the things that Gracia asked was, she wanted to say, thank you so much. Can we learn more about data privacy if we join the Women Who Code Emerging Tech community? What other topics are usually covered there?
Absolutely. So in Women Who Code, we have a new technical track. It's called Emerging Tech. And there we cover all the emerging technologies, from data privacy to AI to cybersecurity, and also blockchain, and even VR, AR. So it's an amazing tech community. We have very inspiring speakers. Please join us and join our Slack and follow our social media, because we have great speakers analyzing everything about the latest technologies.
I love that. I feel like there's just such a wealth of knowledge in that community. And I know that so many of the people that participate and do speak are such experts on their particular subject. So there's just so much to be learned from that emerging technologies group. And I see that Stephanie just popped it into the chat. So if anyone is interested in, learning more about the emerging technologies, hearing more from Maria, you can absolutely check there. I do have another question that popped in. I think we have a little bit more time. So from Zilzan, how do we know that the information excluded from training is not relevant to the model? I think that's the 1, 2, 3, 4 up.
How do you know the information excluded from training is not relevant to the model? I'm not sure I understand the question. So it depends. So let's say that you want, you should exclude from training any information that you think that is not relevant to the model, because there is no reason to revealing this information to the model in the first place. I can understand that sometimes, you need to do some prior analysis to see what features are more beneficial. But if you really want to respect your users' privacy, there is information that you should avoid using in the first place. Please do give us another question if it was not clear. I'm not sure if I answered what she really wanted to ask.
Yeah. And just in case you feel, Zelzan, that answer wasn't fully clear, just another reminder, back to what Stephanie popped in the chat, that was the link directly to the Women Who Code Emerging Technologies track, where Maria is our leadership fellow this year. So she's absolutely available in that chat. So if you do have, more in-depth questions, want to dig further into this, you can absolutely find her there and she can answer those questions for you. And I know we're getting close to our time here. So what I do want to say was I want to thank you, Maria, for presenting on developing privacy preserving software. Your session was, like I said, so informative, so helpful. And I just wanted to say thank you so much for anyone that did ask a question, for being a part of the audience today.